Good morning, class. We are looking at the final exam review covering from chapter section 2.1 to 6.1, chapter 2 limits and derivatives, chapter 3 differentiation rules. The first part covers those chapters. Here's a pledge. Before starting the exam, I expect everybody to read that. I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. In other words, you take the exam on your own. All right, we start with the differentiation formulas. The definition: f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. And of course, there are more information about sign, about e. However, when it comes to differentiation, now we have access to formulas. For example, for the power rule, for trigonometric functions, we can use them. Product and quotient rules, chain rule, exponential functions, logs, inverse trig functions. When we have a curve, as we move from one point to the next, along the x-axis, the distance delta x or dx or bp, they are given. Along the curve, the rise is delta y or bq. Along the tangent line is dy or ab, where dy is f prime of x dx. And linearization means find the tangent line. Logs, as long as we understand the base must be positive and it can't be 1. When we look at log x base b equals y, and this arrow, that means b to the power of y equals x. They have the same base, the same exponent. It gives rise to the following properties. For example, log 1 with any base is 0, log b base b is 1, log b to the power of x base b is x, so on and so forth. If the base is a 10, we call it common log. We don't write the base, and these are the properties for common log. If the base is e, we call it y equals lnx rather than log x base e, and these are the properties. Logs and exponentials are inverse functions. Therefore, they are symmetric with respect to the line y equals x if you graph it. The change of base formula, log x base b, is log x over log b with any base, as long as they are identical. For example, common log or natural log. So log x over log b or ln x over ln b. As you can see, this point has coordinates 1, 0. Now, to the left of that, when x is between 0 and 1, the graph is below the x-axis and it's negative. And to the right of it is above and therefore positive. And when you take the derivative of ln x, you simply flip over, or you write the reciprocal of the argument x. In the case of g of x, the same thing. And then g prime is by the chain rule. If the base is not e, then we tag along 1 over ln b as well. The reverse process of differentiation is called anti-differentiation or integration. FTC, short for fundamental theorem of calculus. There are two parts. The integral of a to x f of t dt, if we differentiate it, we get f of x. That means this function evaluated at upper limit, the lower limit is any number. The integral of a to b f of x dx, this is a definite integral and it's a number, capital F of b minus capital F of a, where capital F prime is lowercase f of x. The substitution rule, f of g of x times g prime of x dx. That means you choose gx to be u, and therefore du becomes g prime of x dx. Is the integral of f of u du, known as the substitution method, which is the reverse process of the chain rule. Now, going to the beginning, speaking of limits, we are interested in, given the graph, find the limit of g of x as x approaches 2, and therefore we look at one-sided limits. The limit of f of x as x approaches a from the left, this notation means from the left. equals L and limit of f of x as x approaches a from the right equals L, then if the two are identical, the limit exists and the limit of f of x as x approaches a becomes L. So because we are interested in 2, we're going to look at the left side and the right side of 2. From the left side of 2, we move towards this point, which has the y coordinate 3. From the right side, we move from this side of 2. We are in this branch. We are moving towards this hole, which has a y coordinate 1. Are they identical? No. Then the limit of g of x as x approaches to d and e does not exist. And we're going to look at the same thing for number 5. And again, we're going to look at one-sided limits. So from the left and right of 5, we move this way and that way. In both cases, we are moving towards this hole, which has the y coordinate 2. They are identical. The limit of g of x as x approaches 5 exists, and it's equal to 2. Also notice, if we assume this is about 1.4, then g of 5, the functional value at 5 is 1.4, which is not equal to the 2, and therefore the function is discontinuous at that point. Reminding you, the definition of a continuity indicates the limit of f of x as x approaches a equals f of x. Then g of x can be continuous at x equals 5 because we are looking at a removable discontinuity as long as we redefine g of 5 to be equal to the limit, which is 2. However, at 2, we have a jump and we can't fix it. And of course, g of 2 is missing. Even if g of 2 is given, it keeps on being unfixable. In other words, okay, you can't fix this because there is a jump here. So I hope everybody's okay with that. You're going to move on, everybody. All right, now we are given a graph and we want to find the limit of r of x as x approaches 2, 5, -3 from the left, -3 from the right. So we take a look at it and see what's going on. 2 from both sides take us down to -infinity. 5, both sides goes up to +infinity. However, -3 from the left goes down to -infinity. From the right goes up to +infinity. And according to definition of a VA, short for vertical asymptote, when the limit of f of x as x approaches a, or a from the left or a from the right, is positive or -infinity, then the vertical asymptote has the equation x equals a. Therefore, this says x equals 2, this one x equals 5, this one x equals -3, this one the same thing, x equals -3. Those are the vertical asymptotes. To find the limit, just plug in and observe. If it gives you any number, you're done. That's the limit. If it gives you 0 over some number other than 0, it's 0 and you're done. If it gives you a number over 0, remember we used to say it's undefined, but now it's infinity or -infinity. And which one is depends on the sign. The sign of the number at top, if the number is positive, it's positive. If it's negative, it's negative. The bottom, 0. From the left is negative, from the right is positive, and therefore it depends on that. And that's why you have to figure it out, and we'll go over an example to make some sense out of it. Indeterminate forms. However, in calculus, most of the time we end up with situations such as 0 over 0, infinity over infinity, infinity minus infinity, 1 to the power of infinity, things of that nature. They are indeterminate forms, which simply put means you need to use your algebraic techniques to figure it out. So various algebraic techniques are in order. For example, the limit of 2x squared plus 8x over x squared minus 16 as x approaches infinity. If you plug in, you do get infinity over infinity. However, the technique is you divide by the highest degree term in the denominator, which is x squared. So if I divide everything by x squared, this becomes 2, this becomes 1, this becomes plus 8 over x, this becomes minus 16 over x squared. Since x goes to infinity, these two go to 0. You get 2 over 1 over 2. However, in general, the best course of action is to approach it by simplifying any fraction you're dealing with, whether it's a rational, and this is the rational expression. This is an example of a rational expression, or it's not. Put it in lowest terms. So let's factor the numerator. As you can see, the top, I can take the 2x out. I get 2x times x plus 4. This is a squared minus b squared. So x plus 4x minus 4. I can drop the common factor of x plus 4, and I get 2x over x minus 4. So I'm going to work on that. Again, in the same manner, because x is approaching infinity, I'm going to divide by highest degree term in the denominator, which is x. This becomes 2, this becomes 1, this becomes minus 4 over x. And of course, this goes to 0, and I get the same answer. In this case, did they make much of a difference? In some cases, it will. And we should pay attention to that. What about this case? First of all, if you plug in, and you can try it, you get 0 over 0 if you plug in. But what we should do, we should always work with the lowest term, everybody. That is the best course of action, which means we are going to work with the factor term. That's the same rational function that we had here. Okay, so we're going to work with that. Now what happens? Just plug in. If I plug in, I get 2 times minus 4 minus 8. Again, minus 4 is minus 8. Minus 8 over minus 8 is positive 1. So when you end up with 0 over 0, in this case, the technique was factoring. So factor. That would be the technique. What about this one? Actually, if you plug in, I hope you see that you get 0 over minus 16, which is 0. But if you work with the factored format, you get 0 over minus 4, and it gives you 0. And in this case, really doesn't make much of a difference, everybody. I want to look at these two cases side by side, because if we work with the factored format, it makes life easier, number one. Number two, if you plug in just 4, never mind 4 from the left or 4 from the right. If you plug in 4, everybody, you get 8 over 0 in both cases. However, 4 from the left or 4 from the right, the numerator is close to 8. In this case, it's 7 point, because it's from the left of 4. That means like 3.999. So it's about 7.999 something. And this one from the right, 8.0001. So both of them are 8 or very close to 8, makes no difference. Remember, every number, both sides are the same sign. So in this case, 8, both sides is positive. If you have a negative number, both sides are negative. 0 is the only number that the left side is negative, the right side is positive. That's why we're going to put 4 from the left. And observe, when we put 4 from the left, for example, 3.9 minus 4 says minus 0.1. So it's 8 over 0 from the left, everybody. And the result is therefore negative infinity. Whereas here, examples such as 4.1, you can even use 5 because you're interested in finding the sign. The sign is positive. So 8 over 0 from the right, it's positive infinity. So I hope you can distinguish between the two. So it's pretty straightforward, everybody. I'm going to quickly recap because I want to make sure that it makes sense to everybody. Number one, the best course of action when you have any fractional format, more specifically rational expressions, factor it and deal with the factored format. However, if you don't do that, in this case, doesn't make any much of a difference. Okay. In this case, may not make much of a difference, but in this case, you will not be able to finish it without factoring. So just to be on the safe side, factor it becomes easier. The same thing here. The limit of 12 over 4 plus 3 e to the power minus t as t approaches infinity, and all you have to do, plug in infinity. And notice, e to the power of minus t, a to the power of minus m is 1 over a to the power of m. So e to the power minus t is 1 over e to the power of t. And because t is approaching infinity, it's 1 over e to the power of infinity, or 1 over infinity, which is 0. So 12 over 4 equals 3 is the final answer, everybody. Plug in, and e to the power of infinity is infinity. This one, e to the power of infinity is infinity. And so 12 is the numerator, the denominator is infinity, because 3 times infinity plus 4 is infinity. Infinity times any positive number is infinity. Infinity squared is infinity. Infinity times infinity is infinity. Square root of infinity is infinity. So it's 0, because it's a constant rather than a number. Part C, because t is approaching negative infinity, becomes identical to part A, because you put 12 plus 4 plus 3 e to the power of negative infinity. That means 1 over e to the power of infinity. That means 0. So it becomes identical to part A, and we're done. T is approaching 0, so plug in. So we are looking at A, B, C, D. We are looking at similar expressions. So e to the power of 0, we know it's 1. So 3 times 1, 3 plus 4 is 7. So 12 over 7 is your final answer, everybody. Now we want to differentiate. We want to switch gears, just reminding you how things work out here. So we are going to differentiate this. And in general, when you're differentiating, whether it's a rational function or a fractional format, and this is not a rational function because the denominator involves e to the power of t. It's a transcendental function. And so anytime the numerator is a number, just bring it up and make it to the power of negative. You don't have to use the quotient rule. Use the quotient rule when you must. So this is 12 when you want to differentiate. So we are going to go with the extended power rule. The derivative of g of x to the power of n is n. So times minus 1. G of x to the power of n minus 1, that means 4 plus 3 to the power of t to the power of minus 1, which makes it minus 2. And then g prime, the derivative of the inside, this is 0. This is 3 to the power of t itself. And so obviously, let's start with this one has exponent -2. So you have a fraction bar, -2 becomes positive and it goes down. And the product of these three, this is -12 with 3 minus 36 e to the power of t over same thing here. The exponent becomes +2. We are done. The limit of e to the power of 3x minus e to the power minus 3x over the same thing with the plus sign in between as x approaches infinity. I hope you realize. If we plug in, this goes to infinity, this goes to 0. This goes to infinity, this goes to 0. So you have infinity over infinity. So the technique we use is the same technique that we use for rational expressions. In the case of a rational expression, we would divide, when x is approaching infinity, we would divide by highest degree term in the denominator. Now, we're going to look at the highest value term because this is not a highest value piece in essence, because it's not a polynomial. So we're going to divide by e to the power of 3x. When we do that, I hope you see you divide this one by this one, you divide this one, both of them become 1. But what happens to this one? I'm going to quickly show you e to the power of -3x over e to the power of 3x equals e to the power of -3x minus 3x, which makes it e to the power of -6x. This is elementary algebra, everybody. And therefore, as x approaches infinity, this piece and this piece, they both go to 0. The answer is 1 over 1 or simply 1, and we are done. So it's pretty straightforward, everybody. What happens here? You get 0 over 0. Let me erase my work first. And I hope you realize if you plug in -4, you get 0 over 0, and you're dealing with a, let me use a different color. You're dealing with a complex fraction. The technique is LCD, which is 4x. So multiply the top as well as the bottom by LCD, and there you have it. When we multiply 4x by 1/4, we get x by 1 over x, we get 4. These two, we never distribute. Here's the reason. X is approaching -4, x plus 4 is a problem, so keep it as a product. You're hoping that x plus 4 will go away, and it does. You get 1 over 4x, and you take the limit of 1 over 4x as x approaches -4, meaning replace the x, and you get -1 over 16. Now, what if I plug in, let me just erase my work. What if I plug in 0? I get 1, because it comes out -1 over 0. So I get 0 over 0. So you have a radical involved, and you know a minus b times a plus b equals a squared minus b squared. So you are going to use the conjugate. The technique is to use the conjugate. And the conjugate for a minus b is a plus b. So the conjugate for the numerator is the same thing. Change the -1 to +1, but you have to multiply and divide by it because this expression must be 1. You can't just multiply by it. And therefore, the numerator becomes the first piece, square root of 1 plus h quantity squared, minus the second piece, 1 squared, and you get 1 plus h minus 1 in the numerator. The denominator you never ever distribute because h is a problem. 1 and -1 cancel each other. H and h cancel each other. And you get the limit of 1 over the square root of 1 plus h plus 1. If you plug in 0 here, you get 1. Square root of 1 is 1 and 1, 2. So 1/2 is the final answer. So in short, this one, you treat it as a rational and you divide by highest value term in the denominator. This one, you need to multiply the top and the bottom by LCD because it's a complex fraction. This one, you use the fact that the conjugate of a minus b is a plus b. You multiply and divide by the conjugate of the numerator, and that will give you the answer. G of x is 1/2 x plus 3 for x less than -2, and it's x minus 1 for x larger than or equal to -2. This is known as a piecewise defined function. Is G of x continuous at x equals -2, y or y not? First and foremost, continuity by definition. Limit of f of x as x approaches a equals f of a. Limit. One-sided limits. A function has a limit at a if the limit of f of x as x approaches a from the left and a from the right are both L. Therefore, the limit of f of x as x approaches a equals L. This is just to remind you what we did. Why are we looking at -2? Each piece is a linear function. For example, the top, you would write it as y equals 1/2 x plus 3. The bottom, you would write it as y equals x minus 1. Every linear function is continuous from negative to positive infinity. Therefore, this is continuous from negative infinity to -2. This one from -2 to infinity. You look at the endpoints. There are 3 things that the continuity says. Look at it, the functional value and the limit. So let's look at the functional value. And before the functional value, you have to go with the equality, and you are going to evaluate the piece that has the equality at -2. So you write x minus 1 such that x is -2. You plug it in and you get -3. Left side limit and then right side limit. For the left side limit, you use the one which says less than. So you use the top piece and you replace the x. So you're going to read it. Limit of g of x as x approaches -2 from the left equals 1/2 x plus 3 evaluated at x equals -2. So plug it. -2 times 1/2 is -1 plus 3 gives you 2. We also look at the right side. The right side greater than. So we're going to use the second piece and we're going to write the limit of g of x as x approaches -2 from the right is to evaluate x minus 1 such that x is -2. Plug in and you get -3. As you can see, the left and right side, they have different limits. The limit doesn't exist. The limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right. Therefore, the limit of g of x as x approaches -2 does not exist. And therefore, g of x is not continuous at x equals -2. However, we could say, is g of x, CTS, short for continuous, at x equals -2 from the right? Notice the functional value and the right side limits are identical. Yes, the function is continuous at x equals -2 from the right. Nevertheless, it remains that it's not continuous at x equals -2, but it is continuous from the right. As far as the terminology is concerned, we want to make sure that it makes perfect sense to everybody. We want to find the limit, and at this point, which we have covered everything, including L'Hopital's rule, you're more than welcome to use L'Hopital's rule, okay? So first, I want to go with the methodology that we discussed in the beginning, the limit of sine theta over theta as theta approaches 0 equals 1. Cosecant, as you know, it's 1 over sine. Cosecant so we write it in this fashion. Also, for this to work, everybody, for this to work, the argument of sine, you can never touch it, you can never change it. The denominator and this must be identical. Because x is approaches 0, so does sine x. So this one is changed to sine x. You have to justify it with this writing. Now they are identical, so I'm going to claim theta can be sine x. So limit of sine theta over theta as theta approaches 0 according to this must be 1. Again, you're more than welcome to use L'Hopital's rule at this point. What about this one? Well, again, we want to go with this methodology. Bear in mind that the argument is x squared and cannot be changed. So if this was x squared, we would be in good shape. So not a big deal. You multiply this one by x to make it identical to that. You also have to multiply the top by x. So now this looks like that. Now we are going to make up two limits, one for x at top and one for the rest of it. So we write the limit of x as x approaches 0, the limit of, so this is this part, okay? And then the limit of sine x squared over x squared as x squared approaches 0. Why x squared? It was x, because when x approaches 0, so does x squared. That's why for this part, we change it. And these three, since they are identical, it follows that it's equal to 1. This is 0 times 1 equals 0. So everything must be justified step by step. If 2x less than or equal to g of x less than or equal to x to the power 4 minus x squared plus 2 for all x, evaluate the limit of g of x as x approaches 1. We use what's called the squeeze theorem. The squeeze theorem says if g is sandwiched between f and h when x is near a, x possibly at a, and limit of those two pieces, limit of f of x as x approaches a equals limit of h of x as x approaches a, and both of them are L, then the one in the middle, the limit of g of x as x approaches a, must be L. This is known as the squeeze theorem. So we're going to look at each side, starting with 2x. If you plug in 1, you get 2. We're going to look at the right side. If we plug in 1, this is 1 to the power of 4 is 1 minus 1 squared is 1. So 1 minus 1 plus 2 is 2. Because these two are identical, the one in between must have the same limit. Therefore, limit of g of x as x approaches 1 must be 2 by the squeeze theorem. You have to mention the theorem. Part B, prove that limit of square root of x brackets 1 plus sine squared 2 pi over x as x approaches 0 from the right is 0. Well, to do so, all you have to do, remember that you can use this squeeze theorem, and we want to come up with this expression. To come up with this expression, anytime you have sinusoidal functions, You can use the trick that sine is always between -1 and 1, sine of alpha. That means sine of anything, alpha, x, y, z, therefore sine of 2 pi over x is also between -1 and 1. Now we want to square both sides. And when we square this one, 1, but the left side we write 0. And why do we write 0? Because class, from 0 to number 1 and from 0 to -1, this area, when you square it, is the same as this area when you square it, because they both become positive. But 0 is included. If both numbers are positive, for example, this is 2, this is 5, this becomes 4, this becomes 25. Okay? But when the number is between negative and positive, okay, then you keep the 0 on one side, and which one do you use when you square the 1? You square both of them, and you keep the larger number. For example, if this is, let's say, -5, when you square it becomes positive 25, it's from 0 to 25, just to let you know. I'm going to erase my work. So having said that, we want it to look like that. What is missing? We need to add 1. So let's add 1. We're going to add 1. This becomes 1. This becomes what we have here. This becomes 2. Okay, so far so good. What else? We're going to multiply by square root of x. And when we multiply by square root of x, you're dealing with an inequality, and it doesn't change because x is approaching 0 from the right and square root of x is positive. So nothing changes. Now this is identical to this one. Now that it is, you look at, by the squeeze theorem, you look at the limit for this guy as x approaches 0 from the right, and this guy as x approaches 0 from the right, both of them become 0. And therefore, the limit of this expression by the squeeze theorem must be 0. All right, so a quick recap for this one. Anytime sinusoidal functions are involved, start with this trick that sine or cosine is between -1 and 1, and then make the expression look like what you want to get, and use the squeeze theorem. The limit of square root of 1 plus 4x to the power of 6 over 2 minus x cubed as x approaches minus infinity. There are different techniques. One would be that you notice that x to the power of 6, if we could take it out, becomes the same as x cubed. So let's factor it from the inside. Reminding you that absolute square root of x squared is absolute value of x. Absolute value of x is distance from 0. It is x if x is positive, greater than or equal to 0, and it's negative x. This means the opposite of x. This means minus x is positive. It doesn't mean negative if x is less than 0. Therefore, odd exponents such as x, x cubed, x to the power of 5, and otherwise, in case of the limit as x approaches infinity for x larger than or equal to 0, square root of x squared equals absolute value of x equals x. In other words, odd or even really makes no difference. If x is approaching infinity, it just comes out. But as x approaches negative infinity, square root of x squared becomes absolute value of x, and it becomes minus x. So in short, if this is positive, it doesn't matter that you have odd or even, makes no difference. But if it's negative infinity, if it comes out as even, it remains positive. It doesn't matter. But if it comes out as odd, see, when it comes out, the exponent is odd, it's 1, then it makes a difference. Therefore, square root of x to the power of 6 is absolute value of x cubed. So we're going to change that to absolute value of x cubed. Since x is approaching negative infinity, and this exponent is odd, then the square root of x to the power of 6 is x cubed if x is positive, and it's minus x cubed if x is negative. X is negative because it's approaching negative infinity. And so now we can divide the top and the bottom by just, this is not a rational expression, but we're going to treat it the same. We're going to divide by highest degree term in the denominator, which is x cubed. And when we do that, first and foremost, the top x cubed goes away, minus the square root. This becomes 2 over x cubed. This becomes minus 1. And now, if you let x approach infinity or negative infinity, makes no difference. This guy goes to 0. This guy goes to 0. This guy goes to 0. And you get 2 over negative 1. 2 comes out. Negative 2 over negative 1 is positive. So be careful when you evaluate this, everybody. Y equals 1 plus sine over x plus cosine x. And we are going to use the quotient rule f over g, which is f prime g minus g prime f over g squared. So y prime is f prime. The top gives you simply cosine x times g, which is x plus cosine x, minus g prime. The derivative of the bottom is 1 minus sine x times f, which is 1 plus sine x. And you just write the bottom intact and square. We're done with calculus. We're going to simplify that, and I'm going to look at a couple of things here. A minus b, a plus b is a squared minus b squared. So that can be replaced with 1 minus sine squared. Also, I'm going to remind you of Pythagorean identities. Sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared, cosecant squared. And we're going to use the first one. If sine squared plus cosine squared is 1, 1 minus sine squared must be cosine squared. So cosine squared and minus cosine squared cancel each other, and we get x cosine x in the numerator. Needless to say, we did the distribution here, x cosine x and cosine squared. And that's the final answer. We are dealing with exponentials. And what I'd like you to know is that in the case of exponentials, the derivative is always itself. D dx of e to the power of x is itself. If it's to the power of kx, is itself times k by the chain rule. If it's to the power of g of x, is itself times g prime. So the answer is itself times what? 5. So if I'm writing this class, I write it as y prime is itself. Then I say, okay, 5. And of course, I put the 5 in front. I'm done. Second one, the answer is itself. By the chain rule, times the derivative of tangent, which is secant squared, and I'm done. This one, I just want to make sure that everybody understands this means 2/3 x. So y prime is itself. And then times 2/3, and I put it in front, and I'm done. What happens when the base is something other than e? Again, the answer is itself, but times ln b. In this case, 3 to the power of x remains, times the natural log of the base, ln 3. And you rewrite. What happens when it's 2 to the power of 7x? we follow that b to the power of g of x is itself 2 to the power of 7x. Any exponential you start with itself. Is the base e? No. So ln b, ln 2. Is this x or t or theta? No, it's 7x. G prime of x. The derivative is 7. And you rewrite it. And you're done. All right. In this case, y equals 4 over the square root of x squared plus 3. Anytime you have a fractional format where the top is a number, you don't have to use the quotient rule. Rather, this one, bring it up. This is x squared plus 3 to the power of positive 1/2 comes up, becomes negative 1/2. Get it ready to use the extended power rule. And so we start with 4, of course, and then extended power rule n negative 1/2. G of x to the power of n minus 1, the same thing to the power of minus 1/2 minus 1. And then g prime, the derivative of the inside is 2x. And we're done with calculus. So first and foremost, the product of these two is negative 2, and this is negative 4x. So this is in the numerator. This goes down with the positive 3/2. In other words, minus 4x over x squared plus 3 to the power of 3/2. And you put it in the same format as square root that we got. So square root of x squared plus 3 quantity cubed. You can put the exponent inside the radical or outside, makes no difference. What about 3x times 3 to the power of x again times? So it's using the product rule, f prime g plus g prime f. So f prime is simply 3 times 3 to the power of x plus g prime. Any exponential, the answer is itself. The base is e, no, so ln 3. And now times f, which is 3x. And we are done with calculus. By the way, this is f of x. I call this one f also because I go with the shorthand notation for product rule. But you can think of this as h of x and h of x, h prime of x here. If that helps, that's fine. Okay. So notice a to the power of m times a to the power of n is a to the power of n plus n. Therefore, this has exponent 1, and this is 3 to the power of x plus 1. This one has exponent 1, and the same thing when we put these two together. So this is 3 to the power of x plus 1, and the same thing we have for the second piece. So this one and this one. So if we factor this one out, this gives us 1, and this gives us 1, whatever is left here, ln 3 times x, and we write it x ln 3. By the way, why do we write it in this format? Because one may think this is ln of 3x, which is not true, okay? Y is x squared plus 4x over x to the power of 6. How do we differentiate that? First and foremost, simplify any fraction if you can. This is x, this is 4. Now, use the extended power rule on that. 6 times x plus 4 to the power of 5 times the derivative of the inside. Although it's 1 and it makes no difference, I like to write it in case it's something else. And of course, you're done. 6 times x plus 4 to the power of 5 is your final answer. All right. 2x plus 3 over x minus 8 to the power of 5. Again, we're going to go with the extended power rule first. So 5 times the same thing to the power of 4. And now the derivative of the same thing uses the quotient rule. So I'm going to go with f over g. So I need f prime, which is 2, times g, which is x minus 8, minus g prime, which is 1, times f, which is 2x plus 3, over g squared, which is x minus 8 squared. Done with calculus, we're going to rewrite the whole thing by distributing here. We get 2x minus 16 minus 2x minus 3, and 2x cancels out the negative 2x. These two add up to negative 19. Now, to be clear what we have, this one is negative 19 over x minus 8 squared. This is 5. I want to make sure we understand this means 2x plus 3 to the power of 4 and x minus 8 to the power of 4. So I'm going to separate them into this format. And now it is clear that the bottom is x minus 8 and the exponent is 4 plus 2, or simply 6. The numerator is 5 times negative 19, which is negative 95 times 2x plus 3 to the power of 4. The reason I wrote this one, just to make this one clear, you don't have to, you can go directly from here to here if everything makes sense and you have no problem with that. Differentiate implicitly, we notice that this is for x squared times y, and we put a raised dot in between, and we call this fg, and we get f prime, which is 8x, times g, which is y, plus g prime, y prime, or dy dx, times f, which is 4x. This one, reminding you of the extended power rule, the derivative of g of x to the power of n is n g of x to the power of n minus 1 g prime, and g is the same as y. Therefore, the derivative of y to the power of n is n, y to the power of n minus 1 y prime, or dy dx. And so never mind the 2. This one would be 2y y prime. With this 2 becomes 4y y prime. E or any other number results in 0. Now we're going to move this one and we make it negative 8xy, and we are going to put these two together. We can take the y prime out, or better yet, 4y prime. So we're going to get 4y prime times x squared plus y. And this one, as I mentioned, goes to the right, becomes negative. All you have to do, divide both sides by whatever is sitting next to y prime, which is 4 times x squared plus y. As you know, these two cancel each other, and we get negative 2xy over x squared plus y. We want to differentiate y equals cosine 3t to the power of 4. As I've mentioned many times before, one easy way is to say cosine and stop. We know the derivative of cosine is negative sine, so negative sine. But if it's x, it's x. If it's not x, g of x, you put g of x. In this case, g of t, you put 3t to the power of 4, because this is meaningless without its argument. Then the derivative of cosine is minus sine g of x times g prime. The derivative is the derivative of the argument, which is 12t cubed. Put it in front. Minus 12t cubed sine of 3t to the power of 4, and you're done. What about differentiating y equals tan to the power of 10 sine of x cubed? I want to make sure everybody understands that this means tangent is being raised to the power of 10. That's why I'm going to rewrite it in this fashion. These two are the same. You don't have to. I want to make that clear. it means tangent has a power of 10. And just to make sure we have no problem doing that, I'm going to call this a function, f of x or g of x or h of x, it doesn't matter. So I'm going to say tangent of f of x to the power of 10. And now something to the power of 10 uses the extended power rule. So we start the derivative of g of x to the power when we start with n, which is 10. Then the same function to the power of n minus 1. The same function tangent to the power of 9. So tan to the power of 9, f of x. And then we want g prime of x. Now we want the derivative of the inside, the derivative of this piece. The derivative of tangent is secant squared f of x. And because it's f of x times f prime of x by the chain rule. Now, we are going to replace the f of x with sine x cubed. So this one becomes sine x cubed. This one becomes sine x cubed. And then what is f prime of x? If f of x is sine x cubed, everybody, what is f prime of x? So take a look at this concept. We want f prime of x when f of x is sine x cubed, but the sine x cubed, the derivative is cosine x cubed. And then times its derivative 3x squared. So this is 10 tan to the power of 9 sine of x cubed. This is secant squared of sine x cubed. And f prime of x is cosine x cubed times 3x squared. So 3x squared and 10, we put them in front, becomes 30x squared, cosine x cubed also next to it, and then we write the rest of them in the following manner. So this one and this one, 30x squared, cosine x cubed, tan to the power of 9 of sine x cubed, secant squared of sine x cubed. And that's the final and easy answer.